So this was the acid titration with the base. So how can I say that is an acid is titrated with the base? You can see the starting pH. The starting pH is low, is less than 7. So that is the reason. It means in the conical flask, what is there? The acid. Acid is here. And in the burette, the base is in the burette, right? And where is the pH meter? pH meter is, where is the pH meter? Yes, it is in the acid. pH meter, the one which is measuring the pH. So you're measuring the pH and then making this graph. It is in the acid. Very good, Asuni. So here is the pH meter. When, what is this point? When the volume of the base added is 0. How to calculate? Is it a weak acid or strong acid? If let's say this pH is near about 3, is it a weak or strong? The pure acid has very high pH. It's a weak acid. How to calculate the pH at this point when there is only weak acid? Only weak acid. So who is controlling the pH? The weak acid. So start asking your questions in case this is not clear. With this we have already done. So I'm just giving you a review because next graph is for a base and we are going to make it. So just a review by the time other students join us. So here is the weak acid. Where is the equivalence point? This one. This pH is more than 7 or less than 7? Is more than 7. Why is it so? Because weak acid is going to give you a strong conjugate base during the reaction. And that strong conjugate base will get hydrolyzed by water to give you OH minus. Even at the equivalence point, there are OH minus. We did discuss all these things. So pH is more than 7 because it's a salt of a weak acid. It's a basic salt. The salt which we are going to get here is a basic salt. And where is the half equivalence point? Where is the half equivalence point? Around 11 here. This is half equivalence point. What is so special about this half equivalence point? Can you see? Is the pH changing? Is the pH changing at the half equivalence point? Is the best buffer? What's the condition for the best buffer? Remember the Henderson equation? pH equals to pKa plus log concentration of A minus over concentration of HA. At half equivalence point, what happens at half equivalence point? Half of the acid is neutralized. So the concentration of HA which is left and the concentration of HA which is converted to A minus is equal. Half of the acid is neutralized. So this is log 1. So best buffer is pH equals to pK. Okay, where can I see the D point? Where is D? Where pH depends only on HA, nobody else is interfering. Where is D? This starting, the weak acid. At this point, you have only weak acid. Yeah, initial, yes. And where is E? Where is E? Where the pH depends only on A minus. It does not depend on HA. It does not depend on the base, the strong base which you are using here. That is the equivalence point. Aditi, equivalence point, right? Okay, what about this? pH depends only on the amount of excess. Endpoint, yes, endpoint. Very good, Aditi. Azuni. Aditi, can you see the difference? Here, pH depends only on concentration of A minus. And over here, it depends on the axis of the base. The base which you are adding. This is endpoint. Endpoint, the color will change because there is a jump in pH, but this is equivalence point. So this question we did last time also, so that's why I'm just giving you a brief review about it. Today we are going to do a new question. This time you have to make a graph. Okay, read the question carefully and let's start making the graph. Okay, for the graph, is the pH curves. We call them as pH titration curves. pH titrations curve means you're doing a titration. Now you know the meaning of titration. And in this titration, you have an acid and a base. And then you have this system. There is a conical flask and there is a burette. So this time, what is there in the conical flask? Yes, what is there in the conical flask? The weak base. Read the question. Weak base. And what is here in the burette? In this burette, what is here? A strong acid. Do you remember a weak base with strong acid is going to give you what type of salt? What type of salt? hmm Weak base with strong acid. No, Azuni, no. Acidic salt. Acidic salt. Because it is the weak base whose conjugate is going to dominate. Okay, I think Lisa, Aditi were answering correct. Sanjana was answering it correct. So a weak base is going to give you an acidic salt. So at the equivalence point, why I'm doing this? Because I want to know my equivalence point is at pH 7, less than 7 or more than 7, right? So where is the equivalence point if it is the acidic salt? Equivalence point means when there is only salt, no acid, no base. Yes, pH will be, that pH will be less than 7. pH is less than 7. Ariba, you are getting it? Just give me 1 second. I have to inform some parents that few of the students have not come. By the time, think about it. Start thinking. Try to make the sketch in your notebook. Okay, I'm back here. So let's start. So what is there in the conical flask? The base is here, right? Base here. And the pH meter is dipped in the conical flask, pH meter. Any question here in this diagram? The base. You are titrating a weak base with a strong acid, right? So acid is the titrant, the standard solution, and base is the analyte. Did I use this word earlier when I was introducing you with the titration? Base is the analyte here. We are trying to identify the pH, or we are trying to work out the concentration of the base, analyte. And acid is the titrant, the solution which we are using in the standard solution, whose pH is known to us. Standard solution. Its pH is known to us, right? Okay, now the pH will be less than 7. Aditi, what are you writing? Because it's acidic salt, right? Aditi, the salt is acidic, so it's going to be less than 7. Okay, you can hear me, children? Yeah. Okay, fine. So let's start. What should I write here? Volume of acid, strong acid, whatever strong acid we are taking. Let's take the acid as Ha, strong acid Ha, volume of strong acid. What's the volume of the acid here? 0. And here I'm going to take the pH. pH of the base in this flask, pH in this flask, where the base is there. So let's see. This is the base, and this is the acid which I'm adding. Let's complete the equation. No, I'm just taking acid, Ha, any generic acid, Ha. It's a strong acid. Base with this acid, I know it's a strong acid. This is a weak base. That's already defined here, right? So what's the product, children? Base, acid, proton transfer. So the product is BH plus and A minus. Any confusion here? Yes, Sanjana, good. Okay. Now, initially, when the volume of the acid added is 0, let's say, because volume of the acid is 0, so whatever concentration, let's say it is 2.5 moles per liter, that's the concentration. What is this? 0, 0, 0. How to determine the pH? How to determine the pH here at this point? From this weak base. So who is going to determine the pH at this point? At this point, when the volume of the acid is 0, the weak base. So when the volume of the acid is 0, the weak base will determine the pH. And for the weak base, if you remember, we have to make the rice tables. Rice tables. You will put base into water. Remember, we calculated we did many questions in which we were calculating the pH of weak bases. BH plus OH minus. Then this is the reaction. Then initial, change, equilibrium, plug in the values. Take the Kb. Kb will be given to you. Use that Kb expression to calculate the OH minus. From the OH minus, get the pH. So initially, at this point, the pH is determined by the weak base because it is the only one who is present. And it's a weak base, so we need a rice table. And we need the Kb value that will be given to you. Okay, so what should be the pH? More than 7 or less than 7? At this point, children, what is the pH? More than 7. Let's say somewhere here, right? Here, somewhere here. Now you started adding drop by drop the acid. Titration has started. You're adding acid. From the burette, you're adding acid, right? Drop by drop. So as you are adding acid, reaction starts. So let's say I'm working with the moles now. Can you tell me why should I work with the moles? I decided to work with the moles. Why? Anyone? Because we are mixing volumes, isn't it? Volume is changing. Mixing volumes. And when you are mixing volume, what happens to concentration? Concentration changes. Remember that. Whenever you are mixing two volumes, you start working with moles or millimoles. Do not work with molarity because concentration changes on mixing volume. Either you calculate new concentration or work with the moles. Any questions till now? What I'm teaching you right now is the next question, next to next question. They all are based on this. So pay attention and keep asking questions. Afan, you're there? I'm sure you have question, but you are not asking. Yeah, no questions, Afan. You're understanding everything. If you if you miss any point, you won't be able to understand anything then. So if you're missing something, if you ask questions, I can cover it. Now I'm adding acid. See this yellow drop acid, I'm adding acid. So let's say I added 1.0 moles of HA. 1.0. This is initial. What is final, children? It's a strong acid, you know, is going to react very strongly. Was final. How much base left? 1.5. How much HA left? 0 is the limiting reactant. How much BH plus formed? BH plus formed 1.0. How much A minus? Oh, yeah. How much? Is also 1.0. Now, what is this solution? Identify the solution, children. These questions we have done earlier also. What is there in the solution? You know that A minus is a conjugate base of the strong acid. So A minus is a weak conjugate base. It's a base of strong acid. Strong acid will give you weak conjugate base. Is it going to do anything in the solution? No. It's not going to control the pH. Nothing will happen. So just ignore it. It's lying there and helping in neutralizing the solution, not doing anything else like a spectator. But what is this? The base, weak base. And what is this? The weak base with this conjugate. So weak base with this conjugate is buffer. So when you started your titration curve from this point and you started adding acid, the solution is becoming buffer. The pH is slowly like this. Can you see? Very small change in the pH. Right? Children, you're understanding that why I'm getting a buffer here? And then let's say I added 2.5 of this. Work with me. 2.5 of this. How much is this? 0. How much is this? 0. So who is there? This 2.5. This one 2.5. What is it called as? What point is this when both of them are 0? When the base and acid are completely neutralized, what is it called as? Equivalence point. This is the equivalence point, right? Who is going to control the pH? What all is there at the equivalence point? At the equivalence point, you have BH plus, you have A minus, you have water. Who will control the pH? This you already know is a weak conjugate base, so it's not going to control. This you know is the conjugate acid of a weak base. It's a strong conjugate acid. So who is going to control the pH? pH plus. And the pH will be slightly less than 7. So all of a sudden at the equivalence point, pH will drop like this. You're understanding the titration curve? So this point, let's say this is the 20 ml. So this point is your full equivalence point. All the acid is neutralized. All the acid is neutralized. So where is the half equivalence point? Is here around 10. Now let's see the situation here when half of the acid is neutralized. Ready? Half of the acid is neutralized. So I'm making the table again. You can see the table here. Half of the base, sorry. This is base. We are doing base titration. Over here is the pH. Let's see when half of the base is neutralized. So I started with 2.5. To neutralize half of the base, how much acid is needed? Half of this. So that is 1.25. So let's say I added this much acid into the solution. I'm adding this much into this base. Initially, no reaction. Finally, how much is this left? 1.25. How much of the HA? It's the limiting reactant. How much of BH plus formed? BH plus formed? Yes, 1.25. How much A minus? Afan? 1.25. Are you interested in A minus, Afan? Are you interested or we can ignore it? Yes, children. Should I worry about A minus amount? A minus, which is the weak conjugate base of a strong acid. Should I worry about this weak conjugate base? No, just ignore it. It's not going to control the pH. You're understanding why I'm ignoring this? Now check in the final situation. What is the concentration of B plus if I say everything is 1 liter? Is 1.25 molar? What's the concentration of BH plus? 1.25 molar. See, both of them are equal. They're equal in amount at half equivalence point. So, and is it a buffer? Yes, it's a buffer. Both of them are there. Strong acid is not there. Strong acid is 0. If strong acid, strong bases are not there, and you have weak acid with this base, weak base with this acid, then it's a buffer. It's a buffer. What's the pH? pH equals to pKa. Oh, it's a basic buffer, children. It's a basic buffer. So I can say POH is equal to pKa plus pKb plus log concentration of BH plus over concentration of B. Henderson equation. But this is equal. So can I say POH equals to pKb? I can say this, right? Best buffer. So half equivalence point is best buffer. So for a base at the half equivalence, POH equals to pKb, which can be written as. So I'm just writing here because there's less space. POH is equal to pKb. You can see my writing here. What is pH? pH is 14 minus POH, right? Or you can say POH is 14 minus pH. Can I write like this? POH. You know this equation? pH plus POH is? Yes, all of you, please type. pH plus POH is? Anil, you are not available for answering today also? Anil. So 14 minus pH is POH. Do you remember the equation? pKb plus pKa is equal to? Yes. This equation also we did. We proved the equation also. Ka times Kb is Kw. So pKb plus pKa is pKw. So pKw is, yes, Sanjana, is 14. Yes, Azuni. pKw is 14, right? 1.0 times 10 is to the minus 14. That is Kw. Take negative log, you get 14. So can I write in place of pKb, pKa minus 14? Oh no, 14 minus pKa, sorry. 14 minus pKa. Don't you think that if you rearrange the equation 14, 14 cancel, you have pH equals to pKb, pKa? So whether it's your acidic solution or basic solution, the half equivalence point where it's going to work like a best buffer, you have this equation valid in both the cases. You can use an acidic buffer or basic buffer, it doesn't matter. If it is basic, you will say this, but the meaning of this is this only. Are we clear about the half equivalence point, children? Okay, now I'm taking you now on the next level. Now I have added excess of the acid. We started with 2.5, you remember? 2.5. Now I'm taking excess of the acid. So I'm erasing everything just to minimize the confusion. Okay, give me some amount of HA so that it becomes excess. Afan, give me some amount of HA. How much should I add? That it should be excess. Means the base should become limiting reactant and it will become 0. How much should I add? Mhm. The base is 2.5. If I want excess of HA left, let's take 5. Initially, when the reaction has not started, these are 0, 0. Finally, the base is 2.5 will become limiting reactant 0. How much acid is left? 2.5. How much BH plus is formed? 2.5. How much A minus is formed? 2.5. That's the final situation in the conical flask. Everything is happening here. The reaction is taking place over here, children, in the conical flask after adding solution from the burette. Reaction is happening here. And this is the final situation. Now tell me, who will control the pH? Remember the line I gave you last time? Whoever stronger, whoever stronger. In some cases, water is stronger. Whoever stronger controls the pH. You remember the pH? Now here, finally, you have HA, you have BH plus, and you have A minus. So according to your understanding, who is stronger here? Who is stronger? If you remember the line here, we are titrating with a strong acid. So who is stronger, children? Yes, answer fast, Azuni. Yes, very good. What about rest of you, Aditi, Lisa, Ariba? Naisha, you were not there in the last few classes. Naisha, you'll find it difficult to understand, but if you want to know something, you can ask questions, okay? You are missing few concepts, so try to understand simple things. So which one is stronger? HA. This is the strongest here. It is fully dissociated. This is a strong conjugate base, but it's not as strong as HA. It's not fully dissociated. It's stronger than water. This is stronger than water. That's it. What about A minus? We already know it's a weak conjugate base. We are going to ignore it again. In these two, I'll say this is the winner. So who is controlling the pH? HA. So what happens to the pH? It will go down like this at the equivalence point. This is the equivalence point. And then after that, this is excess of HA. Is the titration curve clear, children? If it is clear, then I'm going to mark the points here. Check, I'm marking the points. Let's say this is A point, this is B, this is C, this is D, and okay, fine. Answer A part. Now you can answer this because you made the graph yourself. So I'm sure that you can answer everything. Yes, children. Only two answers? Mhm. Okay, what's the pH at the equivalence point? More than 7, less than 7, 7. No, Afan. Afan, it's not 7. It's less than 7 because the pH is controlled by this BH plus because these two are 0, 0. This is the acid. The pH is controlled by strong conjugate acid of the weak base. So it's less than 7. Okay. B part. Only two answers again. The maximum, the best buffer area, best buffering. Yes, it's the best buffering area, right? Somebody asked you, this is the best buffering area. You can see the flat, this is nearly flat. Okay, C. Ariba, you're understanding everything? You're not answering, Ariba. C. Sanjana is saying B. What about rest of you? Remember, this is the half equivalence point. What happened, Aditi? Is it clear? Half equivalence point when the concentration of this BH plus and B are equal. So when you take the log of that, I told you everything in the form of table, and then I was showing you everything there that why this half equivalence point has pH equals to pK. We proved it. D. So this is also B, right? This is also B, and this is C. pH depends only on B, means nothing else is added. Yes, very good. A point. And it's a weak base, so you need a rise table for it. Rise table. pH depends only on BH plus. Perfect, Azuni. Very fast. Here. And because rest all are 0. At the equivalence point here, this is 0, this is 0. So the concentration of BH plus, not the water, because this is stronger than water. It's a strong conjugate acid of a weak base, stronger than water. So you need the rise table for this one. And what is at D here? Oh, we are going on the next F point. So pH depends on the amount of excess strong acid. That is D. Do I need a rise table here to know the pH? Afan, do I need a rise table? No. Why? Because this is strong acid. It's fully dissociated. No rise table needed. You are just going to work with initial and final. That's it. But at this point, I need a rise table for the weak base. Rise table. At this point, I need the rise table for this. So children, what does I need here? Can you check over here? Here, from here to here? What is needed to calculate the pH? Good, Afan. What is needed here? Henderson-Hasselbalch equation. You're going to use Henderson-Hasselbalch equation because when you started adding acid in the weak base, immediately the salt is formed and then there is a base with the salt. It's like a buffer. You can use Henderson equation. So after the A point, your solution is a buffer after this point. After this point. Here, this solution is a buffer. This is buffer area up to here. You are going to use Henderson-Hasselbalch equation to calculate the pH. You're not going to make rice table or anything. Rice table for this part because it's a weak base, pure base, nothing added. But after you started adding the strong acid, immediately reaction starts. Immediately you start getting BH plus and it's a buffer. You can use it for your calculation of pH by using Henderson-Hasselbalch equation. Do you remember Henderson-Hasselbalch equation, all of you? Can you type the Henderson-Hasselbalch equation for pH? Yes, please type it. For this system, Henderson-Hasselbalch equation for pH for this system when there is B and BH plus. pH. Anyone doing it? Mm-hmm. No one? pH equals to, Aditi, you are not answering? pKa plus log concentration. This is an acid equation. So base will be in the numerator and BH plus will be in the denominator. Yes, Aditi. But if I say write on the equation for the base, for the POH, just analyze it. Try to understand and memorize it. If you are working with pH, the acid will go in the denominator over here. But if I say POH, then pKa will become pKb. And then in the numerator, you have the acid, BH plus. In the denominator, you have the base. Yes, Asuni, good. So please understand how to use your Henderson-Hasselbalch equation because in these titration curves, in this area, if you are working with a weak acid or weak base, this area is called as buffer area. One last question based on this titration curve. I want all of you to think and try to answer. From this A, let's say this point is A and this point is B. From A to B, who is the limiting reactant? The acid or the base? A to B. I'm adding acid, you can see. Who is the limiting reactant from A to B? Limiting reactant is the one which is becoming zero. And excess is the other one. Those who are answering base, what's the pH in this area? Is it more than 7, less than 7? If it is more than 7, then how come base is 0? It means the solution is basic, right? It means acid is 0. Whatever acid you are adding, base is reacting and making it 0 every time. In this area, limiting reactant is acid. If limiting reactant is base, then this area is the where limiting reactant is the base. This area. Here you have added excess of the acid. So in this area, limiting reactant is the base. Base is totally 0. And in this area, limiting reactant is the acid. Who is the excess reactant here? Excess reactant is the base. That's why the pH is more than 7 in this area. And in this area, who is the excess reactant? Acid. That's why the pH is less than 7. So you are aware of the limiting reactant, all of you. Limiting reactant is the one who is going to become 0 first. Once it is 0, reaction stops. So reaction is going to stop just because of the limiting reactant is finished. Means that particular reactant is over. If reactant is not there, then no reaction. That's the meaning of limiting reactant. How to identify limiting reactant? Whoever is becoming 0 first in your calculations is the limiting reactant. There are many ways. One more, whoever is giving you less amount of the product is the limiting reactant. So we did all these things in unit 4, I think. Okay. So ready for titration questions? Now, children, I will be doing plenty of writing work here, plenty of calculation work. Please take out your calculators. You people are going to help me. And I will be teaching you many things. So try to understand and keep answering here. The whiteboard will be full of calculations. So don't try to get confused. If something is not clear, if you are not able to make out where I'm writing, ask me, where are you writing? I show you, I'll make a big circle over there. So generally, if you see wherever I'm writing, I'm making a big circle. Stay focused. Everything you know, everything you know. It's only that now whatever knowledge we have gained, we are applying in this question. It's a titration question. Read the question, please. And when you are reading the question, identify what type of acid is this? What type of base is this? And write the equation. Complete the reaction. HClO4, what type of acid? Strong, weak? I told you to memorize only 4 or 5 strong acids. This one is strong or weak? KOH, Aditi, Azuni, Ariba. Please remember, memorize all the strong acids which are needed for AP chemistry. You cannot waste time in the examination in just thinking, is it strong, weak, strong, weak. It's a strong acid and strong base. I've already given you list so many times. Complete the equation. So we are dealing with a strong acid and a strong base. Complete the equation, children. And I'm making the titration setup here? Can you tell me what is there in the burette? Read the question carefully and tell me what is there in the burette and what is there in the conical flask. Yes, children, what is there in the burette? Yes, Azuni, acid is in the flask because acid volume is fixed. You can see that it's 40 ml. So we have taken 40 ml of acid in this flask with this molarity. And what is here in the burette? Is KOH. So when you start the titration, you open it and KOH starts coming and down and getting mixed with the acid here and reaction starts, right? So let's do it. Can you complete the equation? It's an acid-base reaction, children. Give me fast. Acid-base reaction. Afan? Yes, Aditi, very good. KClO4 plus H2O. Perfect. This is acid is going to donate this proton. This is base. OH minus is the base which is going to accept it. OH minus, H plus, water. Good. Okay, and the salt. Now this salt which has come from a strong acid. So let's do some decision for the salt. It's a strong acid and strong base salt, right? Means the K plus has come from strong base and ClO4 minus has come from strong acid. So what kind of K plus? Is it weak or strong? Weak conjugate acid because it has come from strong base KOH. ClO4 minus is a weak conjugate base. So both of them are weak. So who is going to control the pH at equivalence point? Who will control the pH? Yes, water. So what is the pH of the water at the equivalence point? 7. So KClO4 is what kind of salt? Is neutral. It's a neutral salt. Okay, so this is clear to us that at the equivalence point, pH will be 7. So, ready? Let's do A part. In the A part, the volume of KOH added is 0.0 ml. So, who is controlling the pH in the A part? Who is controlling the pH at the A part? KOH is not there. KOH is 0 initially. HClO4. And what's the concentration of HClO4? So can I work with the concentration in the A part? You see, I told you not to work with concentration. But here I'm saying let's work with the concentration here. The reason? Because I have not added anything yet. There is no change in concentration. So the concentration of HClO4 is still the same. There is no change because we have not added any base into it, right? And it's a strong acid. You can write down its dissociation. It's going to dissociate completely to give H plus and ClO4 minus. It's a strong acid, fully 100% dissociated. So what's the concentration of H plus, children? 0.200 molar. Same, because it's 100% dissociated. So this concentration is also 0.200 molar. This one is also 0.200 molar. 1 is to 1 is to 1 is to 1, right? So what's the pH? Is negative log of concentration of H plus, which is, can you work out the pH here? And we'll make the titration graph also. This is the volume of KOH, initially 0, and here is the pH. So we'll be working with the graph here. So who is calculating the pH? Anyone? Take the negative log of concentration of H plus. Pick up your calculators. Plug in the values. And you're getting, I will go for 3 significant figures. Means 0.699. Yes, very good. Azuni, don't round off. Is it? 699. No, Azuni, right? Yes, Apan, come back fast. This is the pH. So in the graph, the pH is very low, right? Somewhere here, it's less than 1, correct? So this is A part, this is A. And you determine the pH of A part just by using the acid. You're not dealing with the base because base is not added yet. It's pure acid, initial pure acid. Let's do the B part. B. In the B part, you're mixing. You're mixing 10 ml of KOH with 40 ml of the HClO4 in the B part. So what's the total volume in the B part? Total volume of the solution. Yes, children? Yeah, 10 plus 40, that is 50. Can I work with concentration now? No. Concentrations are changing. So I will work with moles or millimoles. Do you remember molarity? Here I'm writing here, children. Molarity is millimoles over volume in milliliter. You remember this equation? Or you can say molarity is moles over volume in milliliter, in liter, sorry. So which equation would you like to use? You can use any one of them, but it's better if I use this one because every time the volumes are given to me in milliliter. You can see? So how many from this equation, what are millimoles? Millimoles are molarity times volume in milliliter. We are okay with this equation? These equations. Okay. Now, can you work out? Now we are going to work with the initial and final. And we are going to work with millimoles. So initially, how many millimoles of HClO4 are there? Use this equation. Look at the data given to you and get the millimoles of HClO4. Get the millimoles of HClO4. Yes, please. Fast. Aditi, Lisa. Millimoles of HClO4. Ariba. Are you going to take so much time in the exam? You can do it without calculator also. Take care of significant figures. How many significant figures, Aditi? 3. So don't say 8. Say 8.00. Right? How many millimoles of KOH? How many millimoles of KOH? The molarity is this and the volume is this. So how many millimoles of KOH? 1.00. So how much KClO4 initially before the reaction starts? How much KClO4? Only Aditi is answering. What about rest of you? Oh, you people love writing 00, right? Okay, final. Who is the limiting reactant? You see, one is going to react with one. KOS, 0. This is 0. How much HClO4 left? 7.00. How much KClO4 formed? Is 1.00. Water, we are not interested, is liquid, right? So we can put a dash here. Okay. Okay, Afan. Now, who is going to control the pH? Look at the final. In the final, who is stronger, children? Who is stronger? HClO4 or KClO4? HClO4. But to know the pH, I need to know the concentration of HClO4. What's the concentration of HClO4? These are the millimoles, right? Isn't it 7.00 divided by the total volume in milliliter 50 ml? This is molarity now. Millimoles over ml. How much is this? Pick up your calculators. 0.140. This is 50.0. Molar. So what is the concentration of the H plus? Isn't it same? You remember here is fully dissociated. Concentration of H plus is going to be the same as HClO4. So can I say the concentration of H plus here is the same? 0.140. What's the pH? Get the pH. pH is negative log of concentration of H plus. You know the definition already. So it is 0.854. Yeah. Okay. Is it a buffer, children? Can I say it's a buffer? You know, for the buffer, what is needed? A weak acid with this salt or a weak base with this salt. Do you have a weak acid here? No. This is a strong acid with this salt. So it's not a buffer. So during this titration, you're not going to use Henderson equation anywhere. Okay. So pH is increasing. This is, let's say, 10 ml. So there is a slight increase in the pH because acid is in much amount. The way I did the B part, you people are going to do the C part. Please do the C part. So initially, how many millimoles of HClO4? This amount is not changing. It's still the same. So 8.00. So when you added 40 ml of the base, how much is KOH in millimoles? KOH. Okay. Aditi is saying 4. Children, can you check? Is she right or wrong? You are using this equation, this one, this equation, to know the millimoles of KOH. And is 0.1 molar and 40 ml. So Aditi is very right. Is 4.00. Initially, KClO4H2OR, initially, before the reaction starts, products are 0. Can you just tell me who is the limiting reactant? Can you give me the final situation, children, in which I'm not interested in water? Can you give me these final values? Okay. So, who is the limiting reactant? KOH. And this is 4.00, which is left. And KClO4 is also 4.00. Are you interested in KClO4? You can say no. So who is going to determine the pH now? So from the final check, who is determining the pH? HClO4, strong acid. So it means I need to know the concentration of this HClO4, and the concentration is millimoles, which is 4.00 divided by volume in milliliter. So what's the volume in milliliter at the C point? What's the total volume, children? The way we calculate it here. It is 40.0 plus 40.0. Ariba, you are getting it? Is 80.0. This is the total volume. So what's the concentration of HClO4 in the C point? Is 4.00 over 80.0. How much is this? Molar. Unit will be molar. 0.0500 molar, right? So that's the concentration of HClO4. Is there any confusion here, children? I calculated the total volume for the C point. We are working with the C condition. When 40 ml of this 0.1 KOH is added in this solution. So the total volume is now 80 ml. We are working with millimoles because we are adding volumes. As volumes are added, concentration changes, molarity changes. So we cannot work with molarity. So we started working with millimoles here. You can see here you are working with millimoles. These are the millimoles. Then you are calculating the concentration of HClO4. Now you know it's a strong acid, fully dissociated. So what's the concentration of H plus in the C part, children? Isn't it same? What's the pH? Get the pH. pH is pH is negative log of this value. Negative log of 0.0500. And that is 1.301. So there is further increase in the pH. See, I started with 0.699 in the A part, pure acid. In the B part, the pH is slightly moving up because you are adding a base. Acid is still, base is the limiting reactant because pH is less than 7. But as you are adding more base, acid concentration is decreasing. So pH is increasing. So pH is going up like this. It's going up. But look at the C point. Can I call it as half equivalence, children? Can I say that half of the acid is neutralized? This is half equivalence point. Half equivalence. So if 40 ml is the half equivalence point, where is the equivalence point? At the D. 80 ml will be the full equivalence point, right? So C is the half equivalence, right? So is the word half equivalence clear to all of you? Half means when half of the acid is neutralized. So who is the limiting reactant at the half equivalence point? Please, all of you, look at this equation. I'm asking you to focus on the word half equivalence point. I want you to understand it clearly. So who is the limiting reactant at this half equivalence point? Who is the limiting reactant? The base. Yes. Good, Azuni. This base. Because it's the one which is 0. And which one is in excess? The acid. That's why the pH is still less than 7. Okay. So now moving to the D part. Ready for the D part? Okay. So I'm going to erase this. This data is for the C part, right? Now we are going on the D part. Complete the table, children, without my help. Complete the table. Initial, final. Complete the table. Okay. Aditi is giving us some data. What about rest of you? You are working out the millimoles of HClO4 by using this equation. Then you are working out millimoles of KOH by using this volume and this molarity. Okay. So Aditi and Azuni, both of them have given me the data. What about rest of you? You're unable to calculate it? Question is here, children. We are working with millimoles because we are adding volumes. When you add volumes, you cannot work with molarity. Remember this line. In the examination, these questions will be there, that they will say, add this much acid into this much base. Now calculate the pH. So when you are adding volumes, you have to calculate everything in millimoles and then divide by total volume. So final, what's final, children? Final here, 0.08. Water is okay, right? So who is the limiting reactant in the final? Both of them? Yes, Aditi, good. Sanjana, good. Both of them are limiting reactant, right? If both of them are limiting reactant, who is going to determine the pH? Because this is strong acid, this is strong base, these are weak. So who is determining the pH here? The water. And the pH of pure water is 7. So D point is the full equivalence point. Can you see? pH at the C point was 1.301, right? And all of a sudden, as you are adding more like this, when you reach at the 80 ml of the base, there is a big jump, right? And this big jump indicates that titration is over. Acid is completely neutralized. And the pH at this equivalence point is 7. So what kind of salt is this? It's a neutral salt. It's not going to control the pH, right? Okay, now let's go for the E point. E part. So complete the table again. I'm going to erase everything. Now those who are not answering, can you complete the table? Can you try to finish the table for the E part? HClO4 still the same. Complete the table, initial part. Yes. Again, Aditi, Ariba, Afan. Both same means why? I could not make out your question, Azuni. How much is HClO4 millimoles? You are using this equation, right? How many millimoles? Sanjana, Aditi, only these two answers? Children? Oh. What about rest of you? Lisa, you are not answering today anything? Lisa, are you there? Lisa, are you there? Okay, can you answer now? Is it okay now? Lisa, you can answer now, right? Your keyboard is okay? Okay, okay. Answer it, because if you're not answering, it means you're not doing anything, not understanding. You find it very difficult to understand on your own. Here I'm helping you to understand. Okay, so initially HClO4 are 40 times. You just multiply these two, 8.00 moles. This equation, KOH is zero point 0.1 multiplied by 100. So 10.00. This is 0. Water, we are not interested because it's liquid. It's not going to do anything right now. Now, which one is the limiting reactant? HClO4. How much KOH left? 2. How much KClO4 formed? 8. Water, we can ignore. So who is going to control the pH for the E part? Is it strong or weak? Is this KOH strong base or weak base? It's a strong base. So it's fully dissociated like this. Oh, sorry. KOH is fully dissociated like K plus and OH minus. To know the pH, I need to know the concentration of OH minus. To know the concentration, I should know the total volume. What's the total volume, children? What's the total volume? Total volume is this 100 plus 40, so 140 ml. So what's the concentration of OH minus? Concentration of OH minus, if you look at the equation, they are same as concentration of KOH. And the millimoles of KOH left are 2 left in the final. So it is 2 divided by 140. Can you work out this? And it's OH minus. Get the POH then. And from the POH, get the pH, which is 14 minus POH. So who is doing calculation? So the concentration of OH minus I have calculated. It is 0.0143 molar. And then I'm going to convert this into the POH. I'll take negative log of this answer. So I'm getting POH. POH, and then I'm going to convert POH. No, Azuni, you are right. Then I'm going to convert POH into pH. Finally, we are making a pH curve, right? Not the POH. But my answer is 12.1. I'm getting pH 12.1. So in the E part, pH is 12.1. That shows 12.141. This one. This is the pH for the E part. That shows that solution is strongly basic. pH is very high. Here base is in excess. So the graph will go very high like this. Can see the titration curve here, children? If I make it more accurately, just to show you everything, we started with 0 KOH, and then the graph is going like this. Then there is a sudden jump in the pH going very high. This point is somewhere around 12. This is your 80 ml equivalence point. This is your 40 ml half equivalence point, right? pH here is 7. It's a neutral salt. Is it clear? So this one is simple. Titration of a strong acid, strong base. You are not dealing with buffers. We don't have buffers here. So we are saying, okay, strong acid is in excess. So let's calculate the concentration of H plus. Base is in excess. So let's calculate the concentration of OH minus. That's it. Nothing complicated. A strong acid, strong base titration. And you are getting a neutral salt at the equivalence point. Please remember these points, these words. Now I'm going to make it slightly complicated for you. I'm going to do this question. We can do this also. But this is exactly same what we have done, some difference in the ratio. So you can do it on your own, or otherwise I'll do it in the next class. Now let's see this one. This is the one which is complicated. I want to do one complicated question. Ready, children? Okay. It's going to take time. So let's move faster. So first, read the question. By the time you're reading the question, I'm setting up the apparatus for titration. I'm using a burette and I'm using a conical flask. Burette is with a stand. There's a stand here. Conical flask is on the base of the stand. This is the stand. This one. Okay. So what is there in the burette? What is there in the burette? Read the question and tell me fast. Oh no, dear. You see, volume of the acid is given to you. Volume and molarity. This volume is fixed. Whose volume is changing? Volume of the KOH is changing. So burette is KOH because the burette is the one from where you are adding KOH into the acid. Acid is here. This is the acid. Acid in the flask. Because whose volume is changing? The KOH, and you are changing the volume by adding more and more and more of KOH. Initially you added 0. So that can be done only if it is a burette, if it is in the burette. If it is in the conical flask, then it's a fixed volume. So we are clear about the setup? Okay. Now, what is acetic acid? Look at the Ka value. Is it a strong acid or weak acid? This is acetic acid. Is it a strong? You can say from the Ka value. Acetic acid is strong or weak? Is this Ka value very large? The Ka value. Ka value is small. It's a weak acid. So you should become expert in all these things. If Ka is less than 1, is always weak. Kb is less than 1 is weak. For strong acids and strong base, if you see, I'm not using Ka and Kb. I didn't mention in the previous titration, I didn't say anything about Ka. But here K is important. It's a weak acid. What is this conjugate, children? Its conjugate will be a strong conjugate base. Is stronger than water. So who is going to control the pH when the acid is 0, when the KOH is 0, when you have only this salt in this flask? Who is going to control the pH? The strong conjugate base. So what will be the pH at the equivalence point for this titration? pH at the equivalence point for this titration. Is more than 7. It's not a neutral salt, it's a basic salt, right? Let's see whether we get the pH more than 7. So we are starting the titration. And this titration is going to be tough. Keep answering here. Lisa, you're there? Your keyboard is working? You can type yes or no. Lisa. Children, this is very important. Don't miss it. This is going to cover whatever we have done till now. We have done the buffers. We have done how to calculate the pH of weak acids. We have done how to calculate the pH of salts. Everything is getting repeated here. So please focus. So first thing is, I will write down the reaction. So reaction, the acid is, don't worry, formula will be given to you. If it is not given, you can take it as HA. But generally the formula will be given to you. This is a weak acid, KOH. Complete the equation. All these are aqueous, aqueous. Complete the equation. KC2H3O2 plus H2O. Okay. First, A part. In the A part, KOH added is 0. If the volume of KOH added is 0, there is no change in the concentration of the acetic acid. So I can work with this concentration, 0.200 molar. So I'm not changing. I'm not working with millimoles. Why I'm not working with millimoles? Because concentration of the acid is same. Volumes are not added, nothing added. So there's no change in concentration. Yes, Aditi, good. But this is a weak acid. I know I want to know the pH. It's not fully dissociated. You know that how it's going to dissociate? Partially, there is an equilibrium. You need a rice table, isn't it? You need a rice table to know the pH of a weak acid. I'm making the rice table. This is the reaction. What's the initial concentration of acetic acid? 0.200 molar. How much initially? Now you complete the rice table. Water is liquid. Just ignore it. It's not the part of your Ka. Complete the rice table. 0.20. Oh, change, sorry. Can I write down the equilibrium straight away? By this time, you're expert of writing the equilibrium straight away? Or you want to write change first? Let's write down the change first. Minus x plus x. Keep asking your questions in case you have anything, any doubt, even from whatever we have done. So don't hesitate in asking questions, because if you don't ask questions, if you don't understand, then you're just wasting your time, right? So what's the equilibrium? 0.200 minus x, x, x. What is Ka? K is the concentration of the acetate ions times concentration of the hydronium ions divided by concentration of the acetic acid. The acid, water is not the part. You know the reason, because it's liquid. Plug in the values, x squared over 0.200 minus x. Ka, is Ka very big? Compare your Ka value, this value with this initial concentration. Can I do approximation, children? Approximation means that I can take 0.200 minus x, this value. I can say x is too small. When I'm going to subtract it, then it's nearly equal to 0.200. If I do approximation, then you can see that you are not getting any quadratic equation. Then you can use your simple graphing calculator, or sorry, scientific calculator to get the answer. If you are struggling with the graphing calculator, not able to do anything in that, then do approximation in the exam. You may differ by very few decimal places, and those people can ignore it if they want, right? So what is x? Rather than wasting time in the exam, if you are not okay with graphing calculator, apply approximation rule every time. Then you will not get a quadratic equation. Raised to power 1 by 2. Get the value of x, children. I hope everybody knows that why I'm making the rice table. Yes, who is going to type here? Why I'm using the rice table for the A part? To know the pH. Why I'm using the rice table? Anyone? You see, I started for the A part, I started making the rice table. Why? Mhm. Lisa? And Sanjana is perfectly correct because we are dealing with a weak acid. It's not fully dissociated. So if it is not fully dissociated, to know the concentration, the aim is to know this X. I need rice table. So you people have calculated X and okay. So fine. No units, children. A number without unit has no meaning. So what's the pH? pH is negative log of X. So what's the pH here? What's the pH? 2.72. You can see that is higher than 1. That indicates it's a weak acid. Now let's make the titration graph. I know that we have less time, but we can start this question and we can complete it in the next class. But let's keep doing it. So this is the pH here. Afan, what should I write here? Volume of KOH. And pH is 2.72, slightly higher. See, for that particular acid HClO4, you remember the pH? It was 0.699 initially. So difference in the pH. If it is a strong acid, generally they are starting below 1. If it is a weak acid, generally they are starting around 3. This is around 3, right? So A part is done. A part is done. Let's do the B part. So now we are working with the B part. This time I'll have this problem of the space on the whiteboard. So I'm writing B part here. So just help me in finishing the table for the B part. Now you're adding volumes. So can you work in molarity? No. Work with millimoles. Do you know the equation for the millimoles? Millimole is molarity times volume in milliliter. So work out the millimoles of HC2H3O2 from the molarity and volume given to you here. So how many millimoles? 20 initially. Now I've started working with millimoles because we are mixing KOH with acetic acid, volume is changing. And what's the new volume, children? New volume is 100 plus 50. I'm going to place a decimal with 10. That's a sigfic rule for the volumes for addition subtraction. Okay, so that's the volume of the solution. Okay, now let's check the millimoles of KOH. Yes, please. Millimoles of KOH. Millimoles of KOH are 0.1 multiplied by 50, 5.0. That's the millimoles of KOH. Initially, this is 0, this is 0. Finally, yes, final, children. Who is the limiting reactant here? KOH 0. How much this acetic acid? 15. How much this? 5. Water? Let's ignore it. You know what is it? It's a buffer. Now you are with a buffer. Weak acid with its conjugate, right? Its conjugate base. These two are buffers. For the B part, I will use the Henderson equation. Children, as we have less time, so we'll continue from here in the next class. See you in the next class then. And join the class at the right time because I'm going to repeat these things, make you understand. See you. Bye.